Alright, in this section we're going to work on estimating a population mean this time. Just let me get my colors here. There we go. Alright, so let me silence that. So, in the last section we learned how to estimate a population proportion by building an interval around the sample proportion in which we expect with a very high confidence that the actual population proportion will lie in that interval. We're going to do the same thing for the mean. So we're going to take a sample mean, we're going to build an interval around that sample mean, and with a certain level of confidence, we're going to be confident that the actual population mean lies in that interval. That's our goal here. Now, key concept. We should know that the sample mean x bar is the best point estimate of the population mu. Now, why we kind of talked about that a little bit last time is because x bar targets mu. We should learn how to use a sample data to construct a confidence interval. So we're going to get a sample data set, get a mean, and around that sample mean construct a confidence interval to estimate the actual value of the population mean. We should know how to interpret such confidence intervals. And 3, we should develop the ability to determine the sample size necessary to estimate a population mean. So we're going to build confidence intervals, and then at the end we're going to talk about how big a sample should we have to estimate a mean. Here we go. Now, we're going to go back to what we did in the central limit theorem. The central limit theorem is required here because we need to use z. We need a normal distribution. So the procedure we use has a requirement that the population is either normally distributed or you must have a sample size that is greater than 30. You have to have one of those two to be able to do this section. So here we go. Now, let me move my camera out of the way. There. Margin of error E for estimating of mu. So this is the error that we talked about in proportion. It's just redone for mu. So it's different because we're doing a different estimation, a different error we need here. So E is equal to T, alpha divided by 2. T is something new. We're going to talk about that in just a second. So you have a T alpha divided by 2, number there, times S, that's your sample standard deviation. What we're doing here is we're going to do the case, first of all, where your sigma is an unknown value. So if you look up here at the top in the parentheses, we're going to focus first on when your sigma, your standard deviation of the population, is not something that you know. And then after we do that, then we'll talk about what if you did know it. So if, in this case, sigma is not known, you would have to use T. T is a very special distribution, kind of like Z, but it's called the T distribution. Now, table A3, let me bring that up real quick. Here's table, whoop, where'd my camera go? Here's table A3. This is the T distribution table. It's very similar to the Z table in terms that the middle of the table gives you areas. Okay? Ooh, excuse me. I'm sorry, middle table doesn't give you areas. Middle of the table, in this case, gives you T values. So it's actually the opposite of Z. My bad. Z gives you areas in the middle. T table gives you areas at the edges. So all of these numbers in the middle, let me get my pen. All of these numbers in the middle are actually T values. The numbers at the top are your areas. Okay? And the number along the left, this is called your degree of freedom. If you want to study what a degree of freedom is used for, you need to take another class of statistics. That's a more advanced topic. For now, we're just going to consider our sample size minus 1. So the degrees of freedom is your sample size minus 1. Let me go back to my PowerPoint. So we'll come back to this in just a second. Let's talk about T. T is called the student T distribution. If the distribution of a population is essentially normal, then the distribution of T equals, what you see there, is a student T distribution. I want you to look at this formula. This formula is very, very similar to what we used for the Z formula. The only difference is that we're using S instead of sigma. We haven't used S before for Z. When sigma is unknown, we use S, the sample standard deviation. Because we're using S, that's why we have to go to the T table. The T table is for all samples of size n. Okay? It's often referred to as a T distribution. It is used to find a critical value denoted by T alpha divided by 2. So, to do this, though, you need a degree of freedom. The number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all data. If you want to learn what that means, you can take another stat class and they will cover it in detail. There's actually other forms of degrees of freedom out there. We're going to just do one. Ours is going to be n minus 1 degrees of freedom. So n minus 1 means the sample size and subtract 1 from it. That's all. So it's your sample size minus 1. So what we're going to do is we're going to do examples where we're going to use t, and at the end of this section I'm going to actually go back and talk more about it. So for now, it's just like z, very similar. It still requires you to have a normal distribution for your x in order for you to be able to use t distribution for your x bars, or it requires you to have a sample size greater than 30. Now, alright, x bar minus e, that is x bar plus e. That's going to be your interval that you build. Remember, we're building an interval to estimate mu this time. So to estimate mu, we're going to use our sample mean. We're going to add and subtract our error to build an interval around our sample mean, and we are going to be a certain percentage confident that mu actually lies in that interval. Okay? Now, let's see if we can get into an example. Here's an example. A common claim is that garlic lowers cholesterol levels. In a test of the effectiveness of garlic, 49 subjects were treated with doses of raw garlic, and their cholesterol levels were measured before and after the treatment. So they want to see the effect of garlic on the cholesterol levels. The changes in their levels of LDL cholesterol have a mean of 0.4 and a standard deviation of 21.0. Construct a, well, let's go ahead and write those down. So the mean. Now, this is the mean for who? And the standard deviation for who? It says the changes in their levels. Who are they referring to here? Who is their levels? Well, what we're talking about, if you read this again, we're talking about the 49 subjects. We're talking about the people who actually had the experiment done on them. So we're talking about just a sample here. So this is our sample data. So this mean, this is our x bar value. So you have to start watching out. Sometimes you're going to have population, sometimes you're going to have sample. You have to recognize which one you're dealing with. The standard deviation here, well, again, that's coming from the sample data. So this is our sample standard deviation. This is when we know that sigma is unknown. When sigma is unknown, we have to use the t distribution, not the z. Okay? Now we also have to have either a normal distribution for our original data set or n greater than 30. Well, our sample is of 49 people. Because that's greater than 30, by the central limit theorem, we can continue. We can assume that we have x bar, a normal distribution. And if x bar is normal, then we can use the t. Okay? So you have to have either a large enough sample or normal. Alright, now that you have all of the data taken out of the problem, and you have your requirement satisfied to use t, we are ready to start building our error. Now, how much error depends on how confident you want to be. We want to be 95% confident in our interval. Let me get another color. So we want 95% confidence. This is what is going to determine how big an interval we have. Everything else is fixed. So 95% confidence. We're going to use that. And then at the end, we're going to come back and answer this question. What does the confidence interval suggest about the effectiveness of garlic in reducing LDL cholesterol? So, do I have an empty slide? No. Okay, let me get an empty slide here. Here we go. Okay, so let's just bring everything over that we had. My pen again. My camera back up. Okay, so we had x bar was 0.4, s was 21, our confidence level is 95%. What else did we have? N was 49. We had, so because of this, we had n greater than 30. That was our requirement, so we are able to use t. Now we're using t because sigma is unknown. Sigma is unknown. So I'm trying to make this as clear as I can, and I'm trying. Sigma has to be unknown to use t, and we have to have either normal or n greater than 30. If we have those requirements satisfied, then we're good to go. Let's build our error. So the error is going to be t alpha divided by 2 times s divided by the square root of n. Make sure I copy that right. Yes. Alright. Now, alpha comes from your confidence level. So if our confidence is 95%, then your alpha value is the rest, which would be 5% remaining. So turn into a decimal. So we are interested in t alpha divided by 2. So that's t, well, our alpha is 0.05 divided by 2. So that's t 0.025. Okay? Now, how do we do this? We need also our degree of freedom. So the degree of freedom, df, is n minus 1. Our n was 49. We subtract 1 and get 48. So we're going to look up our degree of freedom and our area to get our t values. Let me bring up the table. Alright, this is our table for t distribution. Now if you look down that first column there, you will notice that we actually don't have our degree of freedom. Our degree of freedom was 48. So what we're going to do is you actually have a gray area here. It's kind of a choice. You could use the closest value for your degree of freedom, or they say you can be on the safe side and you can take the smaller degree of freedom. The smaller your sample size, the more unreliable the data is, so the larger your variation will be allowing for in the t value. So if you go smaller, you're being on the safer side in your interval. It'll be bigger than necessary. If you go on the larger number, then your interval will actually become smaller. It's kind of up to you to a certain extent. If you actually have a question where this happens on my stat lab, I would actually look at the example and see what they do. So according to the book, it's actually a choice. I would recommend that you take the closest value just to continue what you've been practicing from Z, but this should not happen very often. Normally when you have a large enough data set, you usually use Z, but it is possible to use T as well. So what we're going to do in this case is I'm actually going to choose to go with the closest value. So the closest value would be the 50. Now, once you have the 50, you then have to, I'm going to have to scroll to the top to look at these. Go up. Look for your area in the tail. Now, in confidence intervals, you're dealing with two tails because you're going two directions when you build your interval. So you have leftovers on each end. So our tail, alpha divided by 2, is our area. And that is for two tails. Area in one tail, area in two tails. Okay, so alpha divided by 2 is for one of the two tails. So 0.025 is the area in one tail. There, that makes sense. So we have two tails in our problem because we're going two directions. Our alpha gets divided between the two. So if we actually do the division, it would be 0.025. If you look at the second row, that's area in two tails together. So our two tails together would be our alpha value. So you could also look at the area in two tails. It doesn't matter in this case which one you use. You either find the area in one tail or use the total area, which is both tails. Later on in Chapter 8, you're going to have to change that up a little bit. It will matter what you look at. But in Chapter 7, you can use one area or two areas as long as you find the area in the tails. Alright, so in this middle column, we're actually going to go down here. And we're going to go down until we get to our degree of freedom. Come on. It should be right there. So I'm going with the degree of freedom 50. That's closest to 48. And there is my t value, 2.009. Here. So T alpha divided by 2 is 2.009. That is what you're going to need for your error. So our error involves 2.009 times the S, which is your sample standard deviation, divided by the square root of n, which is 49. Now this you could work out by hand, or you could punch in your calculator very carefully. So 21 over the square root of 49, that's 7. So 2.009. So 21 divided by 7, that's 3. If we multiply, we get 6.027. This is the amount of error we are allowing for when we build our interval. So I am going to take my x bar, and we are going to add and subtract the error to get our interval. So x bar, whoops, what is my x bar? I guess I should write that, which they gave that to us, 0.4. 0.4 is our x bar. We're going to add and subtract 6.027. So we end up with x bar plus e equals 6.427, and x bar minus e equals negative, why aren't you writing pen? My computer's doing, whoa, what's it doing? Okay, what if I subtract? Where's my calculator? Calculator. 0.4 minus 6.027. Negative 5.627. So our actual population value mu lies somewhere in this interval between 6.427 and negative 5.627. Now, if you recall, what we were talking about was we were talking about the cholesterol level. So what does this tell us about the cholesterol level? Well, this is the mean change in cholesterol level. Let me go back to the problem. So, this interval is telling us that it could be a positive change or a negative change in cholesterol levels. Or, in the very middle of that is actually the value 0. There could be no change at all in cholesterol levels based on garlic usage. So on the next screen here, I have a summary of what we're talking about. And this summary is a very specific way of stating a conclusion that you can draw from this interval. So the focus is not so much on the creating of the interval, so much as what can you conclude based on that interval. So here we go. We are 95% confident, because that's the confidence level we worked with, that the limits of negative 5.6 and 6.4 actually do contain the value of mu, which is the mean of the changes in LDL cholesterol for the population. Because the confidence interval limits contain the value of 0, it is very possible, because anywhere in that range could be your mean, it is very possible that the mean of the changes in LDL cholesterol is equal to 0. It's possible garlic has no effect at all on cholesterol level. It does not appear that the garlic treatment is effective in lowering cholesterol. Because it could be 0, we have no significant evidence to conclude that it could do otherwise to our cholesterol levels than just nothing. Okay? If our cholesterol levels were all in a positive interval above 0, we could conclude that it makes a positive effect. If they were all the negative number range without 0 in the middle, we can conclude it makes a negative effect on our cholesterol level. But because it includes the 0, we cannot draw any conclusions away from 0. It could very potentially be 0. We have no reason to believe otherwise, because any number in that interval is potentially mu. So that's an example of dealing with building a confidence interval when sigma is unknown, meaning you had to use t. So let's talk about t-distribution, the student t-distribution. Number 1, the student t-distribution is different for different sample sizes. That doesn't happen for z. Z is one bell shape. It doesn't matter if it's a large n or a small n. It's normal. That's all we care about. It is normal. The student t-distribution has the same general symmetric bell shape as the standard normal. Let me show you. Here's a picture of 3 of the standard, or the t-distributions. well, two t-distributions, and then the standard normal. The blue one is the one we usually work with, the z1, the standard normal. The red and the orange are two different t-distributions. Notice though they're both symmetric bell curves. In the middle is the mean of 0. So even for t, the mean of the bell curve is still in the middle and it's still 0, which is number 3. Number 4, the standard deviation of the student t-distribution varies with the sample size and it is greater than 1. Okay, so the t-distribution does not necessarily have a standard deviation of 1. 5. As the sample size n gets larger, the larger the sample size, the student t-distribution gets closer to a normal distribution. So let's look at this. The orange one here had a sample size of 3. The red one had a sample size of 12. The larger the sample size, the closer it becomes to this bell curve at the top, the standard normal bell curve. So the larger the n, the closer we are to a standard normal distribution. Now, if you wanted to find your x bar or your e, so meaning you had a confidence interval, so your confidence interval ranged in this certain interval, so maybe from x1 to x2. That's your confidence interval. What you could do is you could find your sample mean and your error by adding those two limits and dividing by 2, or by subtracting those two limits and dividing by 2. It depends on which one you're trying to find what you would do, but there are cases where you do need to go backwards. Okay? Alright. Now, finding a sample size for estimating a population mean. So, how big of a sample do we need? We did this for proportion. We're going to do this again for mean. Notice the formula is solve for n. This is our error formula. They took the error and they solved for n. Notice we're dealing with sigma here, not s. But we'll talk about that in a second. So, let's see. Notice also we're dealing with z again. What we're doing is we're assuming that we're going to have a large enough sample to be able to work with normal. And we're assuming we have our sigma. Now, do I have an example? Oh, yes. We'll have an example in just a second. So, we need z, we need sigma, and we need e. We're going to do that in a problem. If you have all those, you calculate n. Here's the rounding rule. It's the same thing as we had in proportion. If the computed sample size n is not a whole number, for example, if n is 10.1, round the value of n up to the next larger whole number. So in this case, it would round up to 11. I don't care how close it is to 10. You always round up. Alright, now, what if we didn't have sigma? Because we talked about that earlier. What if we don't have sigma? Well, if we want to find n and we don't have sigma, you have 3 choices. Number 1, you could use a range rule of thumb to estimate the standard deviation as follows. We did this back in chapter 3. The range divided by 4 is a good approximation to sigma. You can do that. Or it's okay approximation. Number 2, you could start the sample collection process without knowing sigma. Just start collecting data. Using the first several values, you could calculate the sample standard deviation S and use that instead of sigma. So remember, you're trying to figure out how big a sample you need. Well, you can start sampling. You can get a small sample and get an S, a sample standard deviation, and use that in place of sigma. That's an option. Or number 3, you could estimate the value of sigma by using the results of some other earlier study. Whichever one you use, it depends on the problem. It depends on what you're doing in life. But you have 3 choices if you don't know sigma. Here's an example. Assume that we want to estimate the mean IQ score for the population of statistics students. How many, okay, that's your question right there. How many? So you're looking for n. How many statistics students must be randomly selected for IQ tests if we want 95% confidence that the sample mean is within 3 IQ points of the population mean? Your confidence level is how you find your z. We're going back to z, remember. You're within. This word within, that is a hint that you're talking about your error here. The only thing we're missing is sigma. So let me write down our formula. N equals z alpha divided by 2 times sigma divided by error, and the whole thing gets squared. Now, Your error you plug on the bottom. That's the 3. Your z. All right, let's review. How do you find z alpha divided by 2 for 95% confident? Well, whoops. What happened? Where did my camera go? There. Well, alpha is the rest. Alpha is the 5%, or as decimal, 0.05. So we are looking for z alpha divided by 2. So divide by 2, 0.025 would be our area in our tail. Draw a picture if it helps you remember. So remember, we're talking about our tail having an area of 0.025. Each tail will have that area when we're talking about confidence intervals and sample sizes. Yeah. Okay, so how do we do this? Well, you have 2 options to find. You could find the negative z-score by looking up this area in the -1 and then writing the positive value because it's symmetric. That's probably the easiest way. So let me bring up my normal distribution. There it is. Alright, so let's go to the negative, and we're going to look up an area of 0.025. Remember, in the z table, your area is in the middle. So our area is 0.025. Right there. So let's find our z-score. Go up and go across. So negative 1.96. So this is negative 1.96, which means the other one is positive 1.96. You always write the positive when you write a z-score, or critical value. So 1.96 is what we plug in for our critical value, and then sigma. Uh-oh, what do we do about sigma? We don't have a sigma. Alright, so I forgot to put it on here, but the book actually talks about this, and I suggest you read your book. It's always good to read the book. In general, in IQ scores, for all IQ tests, the standard deviation is 15. Now this is for the population of all people. We're interested in statistics students only here. So what we're going to do is we're going to use that sigma as our sigma value, as an approximation. So it's not the actual sigma, it's an approximation, but it's based on a larger population than what we're interested in. So this is one of those cases where we don't have our sigma, but we have another one that we can use to approximate our value. Alright, calculator. (96.04). Now, remember, this is a sample size. Are you going to go and sample 96.04 statistics students? No, you can't sample 0.04 of a student. That's not legal. I mean, you'd have to cut a body part off and say, here, this is... No, you don't do that. You always round up. So we would actually need to sample 97 students to get a good estimate with 95% confidence that we're within 3 IQ points of the actual mean. So we're trying to estimate the population mean within 3, being a very small interval, and we want 95% confidence that the mean is in there. There you go, that's a good example. Alright, we have one more part. This section presents methods for estimating a population mean again. But, in addition to knowing the values of the sample data or statistics, we must also know the value of sigma. So we're going to build a confidence interval again, but this time we're going to know sigma. We won't need to use S, our sample standard deviation. We still must have a normal distribution for the population, or the sample size must be greater than 30 to continue. That's still a requirement, along with knowing sigma. Now, if you know sigma, you may find the error using sigma. And if you can use sigma, then you use z. If sigma is known, you use z. You have to have normal, you have to have n greater than 30, but you can use z with all those satisfied. T is only used if sigma is unknown, but you still have to have normal or n greater than 30. Everything else is the same. It's just instead of T, you use Z, and instead of S, you use sigma. So let's try one. People have died in boat and aircraft accidents, can't see, because an obsolete estimate of the mean weight of men was used. In recent decades, the mean weight of men has increased considerably. So we need to update our estimate of that mean so that boats, aircrafts, elevators, and other such devices do not become dangerously overloaded. Using the weights of men from a random sample, we obtain these sample statistics for the simple random sample n equals 40 and x bar equals 172. So we're going to use the sample data to try and estimate what all men's average weights are. So research from several other sources suggests that the population of weights of men has a standard deviation given by sigma equals 26. Notice this is the standard deviation for all men in general. So we're going to actually work with sigma, which means we can work with z. Alright, part A. Find the best point estimate of the mean weight of the population of all men. Well, remember x bar, that was, I forgot, 172.55? That is the best point estimate of mu. So that's it, the answer. Now we want to construct a confidence interval. So I need a new slide. Let me make room here. Alright, so part B. Whoa. Where's my pen? Part B. So we want to build a confidence interval. X bar plus, oops, minus comes first. These formulas are on your formula sheet, by the way. X bar minus the error, and then x bar plus the error. And we are estimating that the mean mu is in here. So this is mu in the middle. Now, x bar is the 172.55. Did I get that right? Yes. All we need to find is e. So we can add it and subtract it. So how do you find e? E is equal to z alpha divided by 2 times sigma divided by the square root of n. Plug everything in. Now, you want 95% confidence, right? That's what we said? Yes. Well, we did that in the last question when we did the n. That was 1.96. Remember, you find alpha, 0.05, divide by 2, find the negative z-score, and just make it the positive, because you want critical values to always be positive. Times, now sigma, they gave us sigma. Let me go back. Yep, there it is, 26 pounds. And divide by the square root of n. What was n? 40. There you go. So, calculator. 1.96 times 26 divided by square root of 40. Actually, I should have done my calculator backwards. There. Equals 8.057. So that's what we need to subtract, and we need to add to our sample mean. So this gives us 180.607, and whoops, that was adding, my bad. Let me do subtracting now. And the subtracting was 164.493. Now your problem should tell you how much to round to, but this is what we're learning here. This is what we found out. We have found out with 95% confidence that the mean weight of all men is in this interval, somewhere between 164 pounds and 180 pounds. Okay? Now, part C. What do the results suggest about the mean weight of 166.3 pounds that was used to determine the safe passenger capacity of water vessels in 1960? So 166.3. Whoops, wrong way. 166.3. That value is still in this interval. So that could still be the actual mean value of adults. But that's on the smaller end. would you rather predict weights to be larger to be on the safe side? Think about that. Here's a nice summary that they have done that types it up all nice and clear of what we learned from this interval. Remember, interpretation is a big part of this course. Based on the confidence interval, it is possible that the mean weight of 166.3 pounds used in 1960 could be the mean weight of men today. It's in the interval. However, the best point estimate of 172.55 pounds suggests that the mean weight of men is now considerably higher. Because that, remember, in your interval, that was on the lower end of the scale. Considering that an underestimate of the mean weight of men could result in lives being lost through overloaded boats and aircraft, these results strongly suggest that additional data should be collected. Probably should look and see if there is a better estimate or a larger sample we can base the estimate on. Okay? So that's what you can conclude from building a confidence interval for population mean. Now, there is a lovely little guide here for how to figure out which formula you need to use. Now, first question, is sigma known? If sigma is known, then you're going to be going this direction. Now, before you can answer how to do it, you must also ask if you have normal distribution. If you have normal distribution, you follow this route, and you would use the z-score formula. Okay? Now, if it's not normally distributed, then you have to ask, is the sample size large? Now, if your sample size is bigger than 30, you're going to go this way and use z. I already said that. Oh, where'd my camera go? If, on the other hand, you're not normal and you're not greater than 30, you go over here. You have to use non-parametric or bootstrapping methods. We don't get to cover that in this course, so you'd have to take another statistics course to be able to do that, build that confidence interval. Now, on the other hand, let's go the other route on this lovely table. If sigma is not known, meaning you're going to use S, then you have to ask, is it normal? If yes, then great, you can use T. If not, then you have to have n greater than 30. If n is greater than 30, you can use T. If not, well, you're back at that other case that you don't know how to do. You'd have to take another class in statistics. So, you have to have normal and sigma. Then you're good. You have to have n greater than 30 and sigma. You're good. Either one of those routes would get you to the z-score. If you don't have sigma, then that's okay. You would have an S. But you still have to ask if it's normal, then you're good. If you have S and it's n greater than 30, then you're good. If not, you cannot do the problem. So you have to have one of these cases to be able to continue. So here's a summary of what we just talked about on that lovely little chart. You use the z distribution if sigma is known. Okay? You use T if sigma is not known. Period. End of story. That tells you which route to go right there. Now, to be able to continue, you must have either normal or a large enough sample. One of those two to go either route. If you do not have normal and you do not have a large enough sample, you're done. You cannot do the problem, and you would actually tell me that. I do not have normal, I do not have a large enough sample, therefore I do not have the tools to finish the problem. And that's the end of 7. So the next video will be Chapter 8. And if you have any questions, let me know. Go get your homework done, because Chapter 8 builds on some of the things we talked about here. So make sure you understand what you're doing before you continue.